Welcome to More Learn, More Teach, where I attempt to simplify the complex. Hello. Today we're going to talk about weak acids and weak bases. Definition of a weak acid base is that it does not completely dissociate or completely ionize in the water when it is put in an aqueous solution. So it will exist in some sort of equilibrium, okay, and they will come in an acid-base pair. So here's an example. So let's say that I have some ammonia, right? Some nitrogen is covalently bonded with 3 hydrogens. I stick that in water. What's going to happen? Okay, I put that in water. Some of the waters will donate one of their hydrogens, right? So this hydrogen might rip off of this guy and attach itself to the ammonia, becoming ammonium, right? So that could happen. That would be described by this equation, where the ammonia plus the water is going to become ammonium and hydroxide. Once it's attached, right, this ammonium will also occasionally deprotonate, right, and protonate this water to make it hydronium. So sometimes you'll have this NH4, right, with the extra proton here. This NH4 will donate that proton to some other water that's floating around. Okay, so that's described here. The ammonium plus the water is going to become ammonia and hydronium. Don't forget, we also have the autoionization of water. The autoionization of water is 2 waters is going to become hydronium and hydroxide. All right, so we have these 3 equations that are going to exist in equilibrium. Okay, so they will have an associated concentration at equilibrium. My ammonia is called a base because it will ionize. It is the one that's going to grab a proton, right? We grabbed a proton with my ammonia to become ammonium. I also created my hydroxide. So the way you can identify that this is going to be a base. In doing so, it also created a weak acid. So my weak acid will dissociate. It will lose the proton, right? It will dissociate back into the base and hydronium. So another way you can identify an acid is because it produced hydronium. We also have the autoionization of water, right? So remember we talked about before that water will auto-dissociate into hydronium and hydroxide at a constant for a given temperature. All right, so now I can define some more terms. So now that I have established that I have these 3 reactions that are occurring in this aqueous solution, I can come up with some relationships between all the different concentrations because I exist in equilibrium. These are not true if I'm not in equilibrium. Okay, so I'm in equilibrium, so I will have a ionization constant of my base. So my base is going to have a constant for the amount of ions it produces based on how much I started with. So I have my ammonium and my hydroxide divided by the amount that I started with, which is my concentration of ammonia. That will give me my ionization constant. So this will be a constant at this equilibrium state. I have an associated dissociation constant for the acid, for the conjugate acid for this base. I will have for what it was started with, right? So I start with my ammonium. So for a given amount of ammonium, right? So this concentration of ammonium, I'm going to produce ammonia and hydronium. So I have a concentration of ammonia and hydronium. That ratio will be my dissociation constant. If I multiply these two together, if I multiply this constant, multiply by this constant, I'll get some number. Well, if I use this algebra, I end up with the concentration of ammonium multiplied by the concentration of hydroxide divided by the concentration of ammonia multiplied by this dissociation constant, concentration of ammonia multiplied by the concentration of hydronium divided by the concentration of ammonium. If I multiply these together, then my ammonia will cancel out, my ammonium will cancel out, and I'm left with the concentration of hydroxide multiplied by the concentration of hydronium, which, if you remember, gives me a constant, which is called the autoionization constant of water. So the reason this all matters is because I can use this property, which I know is equal to 10 to the minus 14. Since I know this is true, I can use this to find whatever I'm looking for. I can find the concentration of hydroxides, I can find the concentration of hydronium, I can find whatever it is I'm looking for. I can use these relationships because I'm in an equilibrium state. I can also look at what happens when I stress one side of the reaction, how that affects all of the others. And we'll talk about that more in a minute. All right, so for our first example, let's see what happens to the pH of our aqueous solution when we add more ammonia to the solution. All right, so for my reaction, my initial reaction, I have ammonia plus water is in equilibrium with some amount of ammonium and hydroxide. So I add ammonia. By adding ammonia, that's going to use, so for every 1 molecule of ammonia, that's going to use 1 more water. I'm assuming the amount of water I have is infinite. It's going to produce 1 ammonium and 1 hydroxide. Therefore, if this goes up, all quantities must go up. All right. Autoionization constant of water is a constant. Therefore, since I raised the amount of hydroxide, the amount of hydroxide is greater. In order for this to be a constant, the amount of hydronium must go down, right? Because if I multiply this by this, if this goes up, this must go down in order to multiply to get the same number. All right, since that's true, the amount of hydronium went down. I use my pH equation. pH is equal to negative log concentration of hydronium. So the amount of hydronium went down. Therefore, the log of the hydronium concentration becomes more negative. Remember that the concentration of hydronium is less than 1, 10 to the minus something. So therefore, the log of 10 to the minus something will be some negative number. So if the concentration goes down, it'll become more of a negative exponent. Therefore, I have a smaller negative number, a more negative number for my log. Negative and negative is positive. Therefore, my pH goes up. This is another example. I want to know the pH of a 2 molar solution of ammonia. I'm given that the ionization constant is 1.8 times 10 to the minus 5. So if we use our reaction, for every ammonia that reacts, it will react with 1 water to produce 1 ammonium and 1 hydroxide. So however much reacts X, the amount of this 2 molar, so not the whole 2 molar, but the amount of the 2 molar that reacts with the water, that amount we're going to call X. That concentration we're going to call X. For every 1 mole per liter that reacts of ammonia, it will react with 1 mole of water to produce 1 mole per liter of ammonium and 1 mole per liter of hydroxide. So this is true, therefore the amount of ammonia concentration that is still there is equal to the amount I started with minus the amount that reacted, or the concentration I started with minus X, X being the amount that reacted. The equation for the ionization constant, which we had before, is equal to the concentration of the ammonium multiplied by the concentration of the hydroxide divided by the concentration of the ammonia that I still have. Substituting in for what we've set up here, the concentration of ammonium is X. The concentration of hydroxide is X. The concentration that I still have is the initial minus the amount that reacted. Therefore, this is my relationship, and that is equal to my ionization constant. This is going to give me this expression, okay? If I multiply through my ionization constant multiplied by the final concentration of ammonia is equal to X squared. The ionization constant multiplied by my initial concentration of ammonia minus the ionization constant times X is equal to X squared. All I did was distribute through my ionization constant. Rearranging the equation, I have X squared plus ionization constant multiplied by X minus ionization constant multiplied by my initial concentration of ammonia is equal to 0. This is an ax squared plus bx plus c equals 0 equation, which has the roots, using the quadratic equation, of x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Plugging in this for the variables that we had here, so a is 1, b is the ionization constant, c is negative ionization constant multiplied by the initial concentration of ammonia. That gives me this expression here. Plugging in all the numbers, I end up with negative 6.009063 times 10 to the minus 3, or 5.9910063 times 10 to the minus 3. Can't be negative, it's got to be positive, therefore the positive root is my answer. So this is the x. The x, right? The x, remember, was the concentration of the ammonia that reacted. It was the concentration of the ammonium at the end, is the concentration of the hydroxide at the end, right? So that is my concentration of hydroxide. This won't give me pH. I have to use the autoionization constant in order to get the hydroniums, because pH is based on hydroniums, not hydroxides. So I use this expression, I use the ionization constant is equal to the concentration of hydroxide multiplied by the concentration of hydronium. Rearrange this equation, and I end up with the concentration of hydronium is equal to the autoionization constant of water divided by the concentration of the hydroxide. 10 to the minus 14, that's the ionization constant of water, divided by the answer we got here, gives me 1.66916867 times 10 to the minus 12. That is moles per liter. This is not my pH. pH equation is negative log of this number, right? So negative log of the concentration of hydronium. That's going to be my pH. So the pH is equal to this number here. We only have two significant figures, so therefore my pH answer is in two significant figures, so my pH is 12. So if I had a 2 molar solution of ammonia, I would have a pH of 12. Now that I showed you the hard way, let me show you the easy way to solve this problem. Easy way. Let's assume that the amount that reacted is very, very small. Right? Let's assume that a very, very small amount, remember it's a weak base, so let's assume that a very, very small amount of my 2 molar solution was reacted, right? So that ionized with the water. So if I assume it's very, very small compared to the original, then that allows me, using my equation for my ionization constant, to now simplify this, because now if I say that very, very small amount reacted, then my initial and final are equal, and I get this equation. Now I can simplify this to x squared is equal to ionization constant multiplied by my concentration of ammonia, or x is equal to the square root of that, which gives me the concentration of hydroxide equal to 6 times 10 to the minus 3. You can see that this is a little inaccurate, right? Because when we did all this calculations, I end up with a possibly more precise number, right? Because some amount did react, but this is pretty close to this when I'm using two significant figures. If I'm using a whole bunch of significant figures, then it'll matter, right? But if I'm only doing two significant figures, it's not going to matter. So now I know my concentration of hydronium is equal to my auto ionization constant of water divided by my concentration of hydroxide, or 10 to the minus 14 divided by 6 times 10 to the minus 3, which is 1.6 repeating times 10 to the minus 12. pH is negative log concentration of hydronium, which is equal to 11.778 blah, 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 blah. Ends up with 12, right? Because again, we have two different figures. But you can see that I was good enough up until 1, 2, 3, 4, 5. I wasn't wrong until I got to my fifth significant figure. So you see that if I only have two significant figures, I can make this approximation and it works. So you really got to look at what is the problem asking you, so you can know if it's safe to make these assumptions or not. I figured I'd finish up by going over a few examples of common weak acids and weak bases. So formic acid and bites. This is the chemical equation for formic acid. Reacts with water to make formate. Formate is the conjugate base for formic acid plus your hydronium. This is the conjugate base reaction. Okay. Acetic acid, vinegar, is acetic acid, reacts with water to give you acetate. Acetate is the conjugate base for acetic acid, and this is your conjugate base equation. Phosphoric acid, found in brown sodas, like drinking sodas. Phosphoric acid is going to react with water to give you your phosphate. Phosphate is going to react with water to give you phosphoric acid, right? So this is your conjugate base for your phosphoric acid. The fancy name for this one is just dihydrogen phosphate. All right, so your bases, you got, by the way, there's a lot less of these common bases. Ammonia is the most common of the weak bases. Pyridine. Pyridine is used in pesticides. It's a poison. You get it from, I think, coal ash. So pyridine reacts with water gives you pyridinium. Pyridinium is your conjugate acid for your base of pyridine. And again, here's your reaction for your conjugate base, your conjugate acid for your base, conjugate acid for your base to give you your hydronium. Aniline, this is used to make rubber. Your aniline reacts with water to give you your conjugate acid to your base of phenylammonium. You see that you have the ammonium here on the end. And again, here's your reaction for your conjugate acid to your base. Methylamine, right, is a fishy smell from putrefaction. Methylamine is going to react with water to give you methylammonium. And of course, your hydroxide. Methylammonium is your conjugate acid for your base of methylamine. Thank you for watching my video. Please like and subscribe. If you have any questions that I can help you out with, I'd be happy to try and answer your questions. Send me an email at morelearnmoreteach@gmail.com.